In this video, we'll be going over rotational inertia, sometimes called moments of inertia in other textbooks. This is the rotational equivalent of mass. It's like what causes it to rotate, what makes it more difficult to rotate. It's in unit 2, when we did F net equals ma, this one's going to be net torque equals I alpha, so we're going to be talking about that I and how we go about calculating it. All right, so now we're getting into rotational dynamics. And before we do that, we're almost there. If we think about our net torque equals I alpha, we've talked about how to calculate this. We've talked about this from our kinematic side. So now we got to focus on this thing called the rotational inertia. And the way you want to think of it is the rotational inertia is how difficult it is to cause it to rotate. That is to say, the harder it is to rotate, it has a larger rotational inertia. So it's the equivalent of mass for linear motion, right? Like if I do F net equals ma, right, we're kind of matching the rotational inertia to mass. Now, the thing about rotational inertia, I'm going to give you some intuition about why this is true, and let me pull up an example here. I have in here my college physics textbook here, all right? And so this is a challenging book. It's a really good book, but more advanced than what you probably need. This is my college physics textbook, and let's say I want to rotate it around my arm here. I want to lift this thing. So this thing has mass. So naturally, the more mass it is, if I picked a bigger book, it would be harder to rotate. Like if I just wanted to rotate around my shoulder and lift it up, I'm rotating it around this point right here. Okay, so this is rotating. However, the mass is not the only thing that matters, right? Also, how far away the mass is from the axis from where I'm rotating. Like if I hold it like this, it's actually much harder, right? I have to put more effort, and it's going to feel like it's harder to rotate than like here. Same mass, same book, but the fact that it's further away makes it harder to rotate. So the rotational inertia is actually dependent on two things. Dependent on both the mass itself and how far the mass is from the axis of rotation. Now, it's not necessary to derive this expression, but basically the definition for the rotational inertia equation, if you go through the process and derive all the rotational motion stuff, which I did in my college physics class, but you don't have to do that, is I equals mr², okay? And this is for a point mass. If I have a single mass of an object and I want to rotate it, r is the distance to the axis of rotation, and then m is the mass. So let's go through and see how we calculate it for different scenarios here. So we have two balls of mass 10 kilograms are stuck at the end of the rod with negligible mass. What is the rotation of the rod plus ball system around the center of the rod? So we make our axis of rotation the center here, and each of these is 10 kilograms. If I want to calculate the rotational inertia, I add up the mr² of every object. So the r to this object would be 4 meters, and the r to this object would also be 4 meters. And so then we would say it is the rotational inertia of this guy is going to be 10 times 4 squared, and the rotational inertia of this guy is also 10 times 4 squared. And so that's going to be 320. And the units of I, because it's mass times r squared, it's kilograms times meters squared. That's the units for rotational inertia, just like that. What if I picked a different axis of rotation? What if I picked an axis of rotation that was slightly off? Oh, this is still 10 kilograms. What if I said I picked an axis? What if I say I try to rotate it around a different location? Let's say this distance here is 2 meters and distance here is 6 meters. Then the rotational inertia in that instance would be like 10 times 2 squared, because that's the distance of the axis of rotation, plus 10 times 6 squared. And you'll find that this will end up being greater. So this would be 40 plus 360, and that's going to be 400 kilogram meters squared. Okay, so as you can see, where the axis of rotation, what are you rotating around, is going to dictate what the rotational inertia is, and that should make sense based on the example we did with the book. Another way we calculate rotational inertia, if we are rotating around, this is a parallel axis theorem. This is something you do need to know for AP Physics 1 and AP Physics C. If we're rotating around an axis that is not the center of mass, we can calculate the new rotational inertia. So imagine by doing this equation here. So ICM is the rotational inertia around the center of mass. So that's around the center of mass. So that means if you somehow know this value already, like somehow I know going around the center of mass of the system, if I were to calculate the rotational inertia, but then if I shift it to a different axis, then you add in an md² term, and d is the distance that you shift the axis. Okay, it's how far the new axis of rotation is compared to the center of mass. So let's go through an example here. So I have a sphere with a mass m and radius r, has a rotational inertia around the center mass equals 2/5 mr². And so that means if I were to revolve it, like kind of like the Earth, if I were to revolve it around the center axis here, and it's spinning like this, going around the center axis, the rotational inertia is 2/5 mr². What if it goes what if I rotate it instead around an axis? I rather than putting it right through the center of it, I instead rotate it around a different line. That's a distance 1/3 r away, and then I revolved it around this thing. So it kind of has this, so like, you know, like when you revolve something around a different axes, like for example, this cylinder, like this piece of tape here, it could rotate around this axis that goes around like this. Let me get it through the center here. Yeah, through the center it would rotate it. But then maybe it rotates around a different axis, right? That's not through the center of mass of the object, but around some other fixed point. Okay, and so what you do in here, and the way the formula works, and it's not super hard, but you got to make sure you know that through the center of mass is 2/5 mr², and then what you're going to add is the mass of the object times how far you shifted the new axes compared to the original center of mass. So this would be plus 1/3 m times 1/3, square this whole thing, md², where that's the distance we shifted. So this is going to be 2/5 mr². This is going to be 1/9 mr plus 1/9 mr². And then 2/5 plus 1/9, I don't know what that's, 18, 19 out of 45. You can use a calculator for that. Okay, so that's how we use the parallel axis theorem. Let's go through another example of showing the parallel axis theorem. So if we have a uniform rod, okay, of length L, and a rotational inertia around the center of mass is 1/12 ml². What is the rotational inertia if you rotate around the end? So rather than rotating, let's say like my pen is rotating around the center axis, I say, what would it take to rotate around the end point here instead, which is a distance L/2 away. Okay, and so that rotational inertia would be the 1/12 ml² through the center of mass plus m times L/2², the distance here that you shifted the axes from the center of mass. Now, you got to remember, this has got to be the center of mass axis. Can't just be any axis, has to be the center of mass, or through the center of mass. And then this is going to be 1/4 ml² because you're going to square the two. 1/4 plus 1/12 is, let's see, that's, well, make that 3 out of 12, right? And that would be 4 out of 12 ml². And that's equal to 1/3 ml². And you might know this formula. Someone might have told you this formula, that rotating a uniform rod around the end is 1/3 ml². And that's how you can find it using the parallel axis theorem. Okay, so those are the two methods that we calculate to rotational inertia when it comes to just point masses, either knowing the point mass or doing the parallel axis theorem. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below, or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.